Hi, welcome back to another physics lesson. In this lesson, we will see the concept of moment of a force. I'll use this lesson to introduce the concept of moment of a force, and in subsequent lessons, we will solve further questions to help us understand it better. The moment of a force is the turning effect of a force about a point. That is, if I have a point here and I'm hinging probably a piece of wood, let's say I'm hinging a piece of wood to this point. Now the turning, and I'm applying a force here. The turning effect of this force is going to be the moment of this force about point O. Now, this force could act in different direction. It could act anticlockwise, it could act clockwisely, and I can have it acting, pulling in this direction. Now, whichever way, and also you could have this force being hinged at an angle to this plane, at an angle theta to this plane. Shortly, I will help us see how to treat each of these scenarios. Now, the first I want us to place, let's have the clock in view. If I have a clock in view, you know that if I have this clock, this is 12, and this is 6, here is 3, here is 9. Obviously, my clock moves in this direction. So whenever I refer to being clockwise, that means I'm talking of this direction. This is the clockwise. Here we say it is in clockwise direction. And whenever I say it is anti-clockwise, that means it is in the opposite direction. And here we say it is what? It is anti-clockwise. So that if I have a force, if I have my hinge, if I have my wood hinge at point O, this is point O, and I have a force acting at it here. From my definition of moment of a force, which is the turning effect of that force, the moment of the force is the product of the force times the perpendicular distance. This is the force F, the perpendicular distance between F and O. Here is the perpendicular distance, D. So, the moment of this force is the product of this force times the perpendicular distance. So, if I have my O and I have my F, if you have the force acting upwards, definitely it will produce an anti-clockwise moment. When I produce an anti-clockwise moment, then my moment is said to be negative. I have minus FD. Now, but if I have it in the other way around, I say I have my O this way, and I have the wood hinge on it, and the force acts downwards this way. Obviously, this will move. If this force is to turn this wood, it will turn in the clockwise direction. So it will produce a clockwise moment. So that my moment now, and there's a distance in the line of the force. There's a distance between this plane, this point, and the line of the force, the line at which the force is acting. Obviously, the distance between the perpendicular distance again is D, and since it is going to come in the clockwise direction, my moment is going to be equals to FD. Now it's going to be positive. Now the third scenario I want you to see is if I have my O and I have the wood hinge at O, but rather than act perpendicular to it, if the force acts in the line of the point is in the line of the direction of the force. Now I have F this way. Now here is the distance. The distance from here to here. Now the force is acting in line. At acting in line, my distance here in this line will become 0. The distance between this point O and the force acting is 0 because the O is in the line of action of the force. So that my moment at this point is F times O, which is equals to 0 newtons. Now I must mention that moment is measured in newtons meter, which is equals to 0 newton meters. For the FD, they are all measured in newtons meters. Now, if the force is now if the force acts at an angle, now look at if it is, this is my O, and here is my wood. Now, if I have the force acting at an angle probably it's acting at an angle theta. Here is a force here acting at angle theta. Now the first thing I want to do is at an angle theta is to resolve this force into different components. Now we'll resolve it into the vertical and the horizontal components. You can make reference, to find how to resolve forces, we have taught vectors. You can make reference to our lessons on vectors and you'll be able to understand how to resolve forces. Now, if this is acting at angle theta, obviously here is theta 2. I have theta here, so that I can now resolve into different components. I have my f of x here, f of x, and I have my f of y. While if you look at f of x and the point O is in the direction of f of x. So the moment about f of x, the m about f of x will be equals to the distance. There's no perpendicular distance, is 0. So that the moment about f of x will be the force f of x times 0, which is equals to 0. So my moment about the f of y, you now resolve the m of y. That will be the moment about f of y, which is f of y times the perpendicular distance, d. Obviously, from here, you know that f of y is the same thing as f sine theta. F sine theta times d that would give us the moment about this particular point. Now let's take an example. Now in this example, we are to find in the figure above the weight of 3 Newton is suspended from y. That is, the weight at y here is given as what? As 300 newtons. Now, calculate the required weight at x to restore balance on the system, neglecting the weight of the bar. Now, we are to calculate the required weight at x, or we are finding moment about this point. Now, the first thing I want us to see is what kind of moment, what turning effect will these forces produce? Obviously, force at y, I should have it what? Clockwise. And for x, I should have it what? Anti-clockwise. So that the moment at y will be positive, while the moment at x will be what? Will be negative. For this balance, for this system to remain at equilibrium, to remain balanced, the whole sum of the moment must be equals to 0. That is, the moment produced by y plus the moment produced by x must be equals to 0. At that point, the system will be stable. Now, the moment produced by y, m produced by y, between y and point O here, I have 102 meters as a perpendicular distance to the point of action. So the moment produced by y is given as 300 times 102 newtons meter. And the moment produced at x also will be given by f of x times 100 in newtons meter. So that my my mx is in the negative, is in the anti-clockwise direction. My my minus mx, because the moment at m of x is going to be negative, will be equals to 0. So that my at the end of the day must be equals to mx. So in place of my, I'm saying that 300 times 102 must be equals to f of x times 100. So that divide both sides by 100, divide both sides by 100. 100 here is 1, 100 here I'm left with 3. 100 here is 1, 100 here is 1. So that f of x must be equals to 3 times 102, which is equals to 306 newton. So that in order to restore balance to this system, I must place a weight of 306 at x. A weight of 306 at x. 306 newton. Now, in our further lessons, we will see how to solve more practical questions on moment of a force. Thank you for staying with me and have a nice day.